This is continuity and one-sided limits. And one-sided limits are best shown with the example. So let's go ahead and look at our first one. So number 1. Have our graph 1, 2. And graph is coming up something like this. Like that. Okay, so this is 2, this is 1, and this is 1. Okay, part A. We've got limit as x approaches c from what looks like the positive power of f of x. Now what that plus means, that's not an exponent. That means we're taking a look at the limit coming from the right-hand side. So as it approaches from the right-hand side. And on this problem, they tell us c is 1. So up here they're telling us c is equal to 1. So we could put 1 in here, so we're studying the limit as x approaches 1 from the right-hand side. Well, here I am coming from the right-hand side. And my x values are getting closer and closer to 1, so it's approaching 1. So we ask ourselves, what is the y value approaching? Well, up here, y is probably like 3 or 4. Gets down to here, gets closer and closer, it's approaching y is equal to 2. So this one will be equal to 2. Let me put that up a little bit so I can... Okay, so that's equal to 2. Now part B says we're taking a look at the limit as x approaches c from what looks like the negative power. And you can probably figure out what that is. If the plus is from the right-hand side, then the negative here will be from the left-hand side. Okay, so we're coming from the left-hand side here and getting closer and closer to x equals 2, so the y value is approaching, or I'm sorry, the x value 1, so it's getting closer and closer to x equals 1. The y value then is approaching 2. When you see it getting real close, you can just come over here to the side, to the y-axis, and see what the y value is. Okay, so C. It's asking the limit as x approaches c of f of x. And put a note here. We saw this in an earlier section, but just to refresh your memory. For a limit to exist, it has to approach the same value coming from the left and coming from the right. Now if I look at this problem, coming from the right-hand side is going to 2, coming from the left-hand side, y values are going to 2, which means my limit is going to equal to 2. So those are my answers. And let me scroll down here. We'll take a look at our next problem. Okay. Actually, let me grab a drink before I start this problem. Okay. And 2, 1. And then 2, 3. And more or less looks like that. And c is equal to 2. So that's where we're studying as x approaches 2. Okay, part A is, okay, limit as x approaches c from the right-hand side of f of x. Okay, so coming from the right-hand side, we're getting closer and closer to x is equal to 2. Well, if I look over here, the y value is equal to 3. Now b, the limit as x approaches c from the left-hand side of f of x. Okay, so coming from the left-hand side, I'm getting closer and closer to x equals 2. The y value, if I come over to here, is equal to 3. Again, for the limit to exist, it has to approach the same value coming from the left side and from the right side. So the limit, as x approaches c of f of x, and c is 2, is equal to 3. Now, if these didn't match, if this was 1 and this was 5, this would be does not exist. Now, notice our graph doesn't even exist at x equals 2. It does. I mean, at this piece, it doesn't exist until down here. So when we're studying the limit, we don't care about what's happening at that value. We're wondering what's happening as it's coming from the left and from the right. Okay, let's take a look at this problem. Got the limit as x approaches 3 from the left side of negative 2 over x plus 3. Well, if you can just plug in this number, go ahead and do that. And this one doesn't cause us any problems. So this would be negative 2 over 3 plus 3, which gives us negative 2, 6, which gives us negative 1/3. Now, if we were to go look at the graph of this, remember the key to graphing these on TI3, TI4 is if you have more than a single number or a single variable in the top or bottom, put parentheses around it. So we're going to go to y equals, clear if you have anything on the y1, and we'll put in negative 2 divided by, and I'll put parentheses right at the bottom, and then we got x plus 3. And then I'll press graph. Now here, we're looking at the limit as x approaches 3. Well, over here at x equals 3, you don't see any real issues. Where the real issue is over here at negative 3. That's where we'd have a problem. So, again, if you got one-sided limits, if you can just plug that number in, and it's fine, then go ahead and do that. Okay, let's look at this one. So we got limit as x approaches 5 from the right-hand side. 5 minus x over x squared minus 25. Well, if I put 5 in there, I'm going to have 5 squared, which is 25, minus 25, which would give us 0. So we'd have a 0 in the denominator. So we can't just plug this one in. But we looked at this method in an earlier lesson. If you can factor the top and the bottom, then go ahead and do that and see if something will cancel. Well, the top is just in the wrong order. We need to have it in standard form, so I'll rewrite this. I'll put the negative x first and the 5 second. The bottom is the difference of two squares, and it factors as x plus 5 times x minus 5. Now, the bottom part's factor as much as we can, but the top part we can factor out of GCF. Remember, if your first term is negative, you always want to factor out a negative. So we got limit as x goes to 5 from the right-hand side. Take out a negative 1, and that gives us x minus 5. So then we've got x plus 5, x minus 5. Now remember, after you factor the top and factor the bottom, if you can cancel something, go ahead and do that. These x minus 5 is going to cancel. That's from the right-hand side, so I have negative 1 over x plus 5. Now notice after I cancel out the x minus 5s, I can actually plug in this 5 now, can't I? So this is going to be negative 1 over, and if I put 5 in there, I got 5 plus 5, which gives us negative 1/10. Okay, now if I were to graph this original problem up here, go back to y equals. Y equals, press clear, put parentheses on top, 5 minus x, close parentheses, divided by, parentheses around the bottom, then x squared minus 25, close parentheses, and then graph. Now as we look at the graph, we're looking at the limit as x approaches 5 from the right-hand side. Well, over here at x equals 5, I don't see any real issues. There is an issue over here. But that's, if I were to set the denominator equal to 0, I'd see that's x equals negative 5 where I have a problem, not 5. So again, this is one where it shows you you can use some of the methods we learned in the previous lesson, factoring and cancel, and then you can plug in a number. I'm not sure if I have room for this one. Let me save this page, and then we'll take a look at that one. Okay, so we've got calc 1, continuity.
Avast virus database has been updated.
One-sided limits. Page 01.pdf. There we go. Go away, Avast. Go away. There it goes. Wasn't wanting to go away. Okay, so we looked at direct substitution. We looked at the factoring canceling method. Let's look at the example of the conjugate method. Okay, so we got limit as x approaches 4 from the left-hand side. Square root of x minus 2 over x minus 4. Well, definitely if I plug 4 in, I'm going to have problems. 4 minus 4 gives 0. Can't have a 0 in the denominator. This is one where we got a radical up on top. And we're going to try to multiply the top and bottom by the radical of the top. See if that helps us any. Or I heard a noise in the house. It's wondering if my stepson was home. Multiply by the conjugate of this. So the first part is the same, and the last part is the same, but the sign in the middle changes. So square root of x plus 2, and this will be square root of x plus 2. Yeah, that or somebody's breaking into my house and stealing everything. But that's okay. I got my PS3 in my room here, so that's the important piece. Okay. Now, again, conjugate, the first part and the second part are the same, sign in the middle is different. If you got conjugates, all you have to do is multiply your first parts together and your last parts. Well, square root of x times square root of x gives us x. Negative 2 times 2 gives us negative 4. Now, you don't actually multiply the bottom parts together, you just put them next to each other. Because we're hoping that what was causing us problems will disappear, that x minus 4. And actually, now that I've multiplied top and bottom by the conjugate, I see the x minus 4s do indeed disappear. So we got limit as x approaches 4 from left-hand side of 1 over square root of x plus 2. Well, now there's no problem plugging in 4, so we'll go ahead and do that. So we got 1 and square root of 4 plus 2. Well, square root of 4 is 2, so we've got 2 plus 2, or 1/4 is our answer. Let me grab a drink, and then we'll take a look at this one. Okay, so we got limit as x approaches 3 of f of x, where f of x is equal to x squared minus 5x plus 1. X is less than or equal to 3. And negative x squared plus 4x minus 8, where x is greater than 3. Well, notice that the limit I'm studying, limit as x approaches 3, happens to match where this changes. Changes from looking like this to looking like this. Now, if that's true, then what you're going to do is you're going to plug your 3 into each piece and see if they're equal. If they're equal, then that means your graph has met. So let's go ahead and do that. So we're going to plug in x equals 3 into each piece. So this piece we got x squared minus 5x plus 1. And then we got negative x squared plus 4x minus 8. So we're going to have 3 squared minus 5 times 3 plus 1. So we've got 9 minus 15 plus 1, which gives us negative 5. And if I plug it in here, I got negative 3 squared plus 4 times 3 minus 8. So negative 9 plus 12 minus 8, which gives us negative 5. Notice these are both the same. When we're studying this limit, this is x is less than or equal to 3. This is coming from the left side. This is x is greater than 3. This is from the right side. And they both approach the same value. So, my limit as x approaches 3 of f of x is going to equal to negative 5. Now, if I was studying the limit as x approaches 1, it wasn't the same as this value right here. Well, x approaches 1. 1 is less than 3, so we would actually just plug it into this piece, and that'd be our answer. Now, there's one case where you're looking at piecewise functions where you can't say this. This is where you got something like this. F of x is equal to, and I don't know, you got 3x minus 1. X is not equal to 2. And then this would be, I don't know, 10, for example, when x is equal to 2. Now here, this is the case where you got a line here, except for there's a hole in it at 2, and a hole then it appears up at 10. Well, coming from the left side and from the right side, if I was studying the limit as x approaches 2, I wouldn't want to plug it into both pieces, because it actually, since this is a line and it's just got a hole in it, we're just plugging into this piece. So the limit as x approaches 2 of f of x, again, we don't care what's happening at 2, we care about what's happening coming from the left and from the right, which is this one. So this would be 3 times 2 minus 1, which would give us 5. So that's kind of the oddball case with piecewise functions. Okay, let's look at this one. Get limit as x approaches pi over 2 of tangent x. And let's see, unit circle. And I'll choose this one. Okay, so let me have that up and running. Okay, well, first thing we try to do when finding a limit is just plug the number in and see if that works. So let's try that. This is tangent pi over 2. We're not saying it's going to work, but we're going to try it. Now remember, your tangent on your unit circle is y over x. Now at pi over 2, we got y. Where it is. Pi over 2, y is 1, and x is 0. So that would give us 1 over 0. So this is actually undefined. So the limit does not exist. Now, the reason why I know it doesn't exist is this is actually an asymptote if we look at our graph. But you can't necessarily just say because there's a 0 down here it does not exist. You have to actually study it coming from the left side and from the right side. It may not actually exist right here at that value, but again, we don't care what's happening at pi over 2. We're looking at it coming from the left side and from the right side. But, like I say, if you know what tangent looks like, then you know why I wrote that down. Okay, I want to make sure my calculator's in radians first. Let me just press mode. And mine is in radians. If yours is not in radians, down arrow, put your flashing cursor on radians and press enter. And then do a second mode to exit out. Second mode takes you have anything in your calculator. I'll press y equals, press clear. I'll do tangent, and then I'll put in x. Now I'm going to choose zoom, and I'll choose z trig, number 7. Okay. This is our graph. Clear over here is 2 pi. Clear over here is negative 2 pi. Of course, this is 0. So right here is pi, and this is pi over 2. And you see that I got a vertical asymptote here. Your graph comes up, skims it, but never touches it or crosses it. And you see coming from the left side, it's going to positive infinity, and coming from the right side, it's going to negative infinity. So it definitely doesn't agree. So it helps to have a little bit of understanding what the graphs look like. And if you don't have that, then graph it and see what your calculator shows you. Now, you can't trust everything the calculator gives you, but some of your very basic graphs like this you can. So again, does not exist. Okay, let's look at the next one. Limit as x approaches 3 from the left-hand side of natural log of 3 minus x. Now this is another one. If I put 3 in here, 3 minus 3 is 0. You can't have log of 0. But let's graph this and see what it looks like. So we're going to do natural log of 3 minus x. So I'm going to press y equals, press clear, push my natural log, and 3 minus x. You don't need a closing parentheses at the end, but I'll go ahead and put it. And I'll do zoom, and I'll choose z standard, number 6. Sets our sets our calculator back to your standard window from negative 10, 10 on the x and y. Now the TI-3, TI-4 lies about logs. It looks like it just stops. It doesn't. It keeps going down forever. Now it keeps going down forever. It's getting closer and closer to this line here, which kind of tells you what that is. But we're looking at this only as it comes to the left-hand side. Well, here I am coming from left-hand side, coming from left-hand side, coming from left-hand side. If you didn't know the fact that it was supposed to go forever, you'd think that if I went over here, this would give me my limit. But it's actually going to negative infinity. Now my actual limit doesn't exist. Limit as x approaches 3, because it has to agree come from the left side and from the right side. And obviously, coming from the right side, it doesn't even exist over here. So it can't be approaching the same value. But our answer there is negative infinity. Let me save that. Okay. And time for my tablet to blow up. It's okay, time for me to get a drink too. Okay, so let's look at our next problem. This gets into the next type, which talks about where something's continuous and discontinuous. Continuous is where the graph exists, basically. Okay, so we got f of x is equal to 5 over x minus 4. Now, if we're talking about continuity, and we're dealing with fractions. Now, fractions can also include tangent, cotangent, cosecant, and secant. Now, if you're wondering, oh, well, how in the world does that include those? Well, tangent I can rewrite as sine over cosine, and cotangent I can rewrite as cosine over sine. Cosecant I can rewrite as 1 over sine, and secant I can rewrite as 1 over cosine. So actually, these can be written in fraction form very easily, and then we can find out where they're undefined at, where they don't exist. Okay, so if you got fractions, what you're going to do is set your denominator equal to 0 and solve. And what you come up with, this is where it's discontinuous. So that's where it's discontinuous. So let's look at this example then. We got a fraction, and the instructions are saying find the x values which f is not continuous, which of the discontinuities are removable. We'll talk about removable here in a second. So I'm going to set the denominator equal to 0. We get x minus 4 is equal to 0. Solve it, and we get x is equal to 4. This right here, and I know that's not appropriate abbreviation, but we'll go with it. That's where it's discontinuous. It doesn't exist at 4. If I were to put 4 in my original problem, 4 minus 4 is 0. Can't have that. Well, let's look at our graph. Now that we have an example in front of us and talk about continuity. Okay. I press my y equals, press clear. I'll do 5 divided by. I want to put parentheses around the bottom part because it's more than a single variable, single number. And then x minus 4, close parentheses, and then graph. Okay, as I look at this, I got a big gap here, don't I? So obviously it's discontinuous here. Continuous is where your graph exists. Well, it doesn't exist, you know, right here at this point. That's actually a vertical asymptote, which we'll talk about. So that's what we're finding. We're finding discontinuity. Something's nice and continuous. Just you can take your pen and just trace the graph from the beginning to the end. There's no places where you have to pick up your pen. Okay. Well, let's talk about removable and non-removable. And I'll show an example here. Okay, I got f of x is equal to let's see, x squared minus 1 over x squared minus 3x plus 2. Okay. Well, if I factor the top and factor the bottom, this becomes x plus 1, x minus 1. Difference 2 squares, dots. That's not very... Try that again. Try to write legible. So difference 2 squares. This one is the PST method. So it factors as x minus 1 times x minus 2. Okay. Now remember with our what we just said about our continuity and fraction. Set denominator equal to 0 and solve. Okay, so if I set x minus 1 equal to 0, and I'll set x minus 2 equal to 0, we're going to get x equals 1, and we'll get x equals 2. Without a doubt, these are discontinuities. Now, if I factor the top and factor the bottom, I notice that the x minus 1s will cancel away. And we're going to be left with x plus 1 over x minus 2. Now, the x minus 1 canceled away, didn't it? I removed it, which means that this x equals 1 here is removable. Discontinuity. And this one isn't removable, so it's a non-removable, if that's a word. So again, this one canceled away, so that x minus 1 was removable. This x minus 2 stayed there, so it is non-removable. Well, let's look at the graph of this, see what in the world we're talking about graph-wise. Again, we need to put parentheses around top, parentheses around the bottom. So I'm going to come over here, press y equals, press clear. Put parentheses around top. And we got x squared minus 1. Close parentheses, divided by, beginning parentheses, x squared minus 3x plus 2, closing parentheses. Graph. This is what our graph looks like. Okay, so let me scroll down a little bit here. Oh, by the way, on this one, before I scroll down, there's no way I can factor the top and factor the bottom and have that cancel, right? So this is non-removable. So that's not going away. Okay, so if I look at the graph of this one, this example, okay, so we got this here. And where's that pass? Okay, right there. More or less, doesn't matter, be precise. Okay, now we said it's a non-removable at x equals 2. We actually have a vertical asymptote there. And you see how we have one piece going up like this, and we have one piece going down like this. Now this other one that's removable is at x equals 1. What we're going to find there at x equals 1, there's an open hole in our graph. Now the TI3, TI4 will not show that, but that's an open dot. Doesn't exist there. Now I like to think of it this way, when we're talking about removable and non-removable. If you can just put a dot right here and very easily make this continuous, that's removable. Now this piece going up here and this piece going down here, this wouldn't be very easy. I'd have to grab this with one hand, grab this with another hand, bend it, and twist them around to get them to meet. That's non-removable. So again, you can kind of use that as your guideline. And I stole that from a book, so don't think that's my idea. That was the author, what they said, the way to think of it. Okay, let's look at the next type for continuity. Guess I better scroll down here. And we got number 10, which is f of x is equal to x squared plus 3x plus 5. Okay, so if we're talking about continuity, and we're talking about polynomials, we're talking about sine, cosine, and we're talking about e to a power, typically. If you got any of these, then there's no discontinuities. I'll probably misspell this many times. I start out pretty good, and then I screw it up. Okay, well this is a polynomial, so there's no discontinuities, and I'll abbreviate it like that. Which, if there's no discontinuities, then they, it can't be removable or non-removable. Okay, let's look at this one. We got a fraction. Well, we know how to handle fractions. We talked about that up above. So let's go ahead and do this one. We got f of x is equal to 2 over x squared plus 3. We said whenever you have a fraction, we set the denominator equal to 0. So I'll set x squared plus 3 equal to 0. Take 3 over to the right side, becomes a negative 3. Square root property from college algebra. If you got something squared equal to the other side, you drop your squared and you put a plus minus square root around the other side. But what a negative gives you inside of a square root, it gives you an I. What that means is if you get an I when you set the denominator equal to 0 and solve it, that means there is no discontinuities. It's continuous everywhere, from negative infinity to positive infinity. Okay, let's look at this one. Got f of x is equal to 5x plus sine x. Well, 5x itself is a polynomial, and sine x, of course, is sine. And we'd said already there's no discontinuities. So if there's no discontinuities in this piece, there's none in this, then there's no discontinuities total. Now, this does not mean that every problem has a sin x in it is going to have no discontinuities. If you have a problem where you have the sin x in the denominator, well, you have a denominator. You have a fraction. So then you have to worry about that. Let me save this. Okay. Page 3. And let's look at our next problem. We got f of x is equal to x plus 4 over x squared minus 16. Well, I can see I can factor the bottom part, sorry. That's the difference two squares. So this becomes x plus 4 over x plus 4 times x minus 4. Well, we said whenever you have a fraction, you'll set the denominator equal to 0. So we'll set the denominator equal to 0. Now, zero factor property from college algebra, if you get 0 on one side and you factor the other side, you set each factor equal to 0. So I'll set x plus 4 equal to 0 and x minus 4 equal to 0. And we get x is equal to negative 4 and x is equal to positive 4. Now, these are where it's discontinuous. Let's go back to our original problem here. After we factored the top and factored the bottom, I noticed that the x plus 4 here will cancel with this x plus 4. So we got 1 over x minus 4 left. Okay. The x plus 4s, I canceled them, didn't I? I removed them. So the x plus 4 over here, this is going to be a removable discontinuity. Now this, the x minus 4 stayed. So the x minus 4 here is going to be a non-removable. Now if I were to graph this, what I would see is the removable. I don't even notice anything weird at negative 4. It's actually a hole in our graph. I don't know what this graph looks like, but it'd be a hole in our graph. Oops. You know, you'd have something like that. When you have a non-removable, that's actually going to be a gap. And oftentimes you'll have one part of your graph going up to positive infinity and the other one going to negative infinity. So they're not asking us to graph those, but extra trivia you can throw up at parties. Make yourself life of the party. Okay. So number 14. We got f of x is equal to 3x minus 5 and x squared minus 3. And we got x is less than 2 and x is greater than or equal to 2. Let's talk about continuity of piecewise functions. Well, first thing we're going to do is check the continuity of each piece. So check the continuity of each piece. Well, if I look at 3x minus 5, that's a polynomial. That's continuous everywhere. No discontinuities. The x squared minus 3, that's a polynomial. That's continuous everywhere. No discontinuities. So we're fine there for this particular problem. Now, it looks like this when x is less than 2. It looks like this when x is greater than or equal to 2. So it changes over. So if I have a graph that's coming here, and this is where it changes. Looks like this going up to there, and then from there on it looks like that. Well, they'll be continuous if these two pieces meet. You could have this situation. You have this one looking like this, and then this one continues down here. Obviously, I have a gap in here, don't I? So this would be where they don't meet. This would be non-removable, right? Because remember, whenever you have a gap like that, that's a non-removable. Now there's one oddball case we'll talk about that's removable for piecewise functions. But again, what we're going to do here is check the value where the pieces change over. Again, what I'm talking about there is where they change over to the other piece. Okay, so let's plug in our x equals 2 into each piece. So if we put it into 3x minus 5 and x squared minus 3, we're going to have 3 times 2 minus 5, 6 minus 5, which gives us 1. And if I put 2 in here, I'll have 2 squared minus 3, which 2 squared is 4, 4 minus 3 is 1. These are the same, which means there's no discontinuities. And that's what they're asking. They're saying which words, find out where it's not continuous, which of the discontinuities are removable. These are both, I'm sorry, this one's, quit watching TV and do my video here. There's no discontinuities, so they're not removable or non-removable. There's no discontinuities. Okay, let's look at our next one. One of my favorite shows is on The Big Bang Theory. I may have to, well, actually this video process after I get done with this, so that'll be good. I can watch that. 7x plus 3 and x squared plus 4. And this is when x is less than 1, and this is when x is greater than or equal to 1. Okay. Well, I'm going to look at each piece. If I look at 7x plus 3, it's a polynomial. There's no discontinuities. It's continuous everywhere. Negative infinity, positive infinity. The x squared plus 4, that's a polynomial. There's no discontinuities. It's continuous everywhere. So we're wondering about where it changes over. What's happening at 1? So if I plug it in the 7x plus 3, and I'll plug it into the x squared plus 4, I'm going to get 7 times 1 plus 3, which gives us 10. And over here I'll get 1 squared plus 4, which gives us 5. These are not the same. So that means this is discontinuous at x is equal to 1. And piecewise functions will pretty well always be non-removable, except for one example I'll give you. So these are non-removable. There's a gap there. Now, if I had, let me show it graphically. If I had this graph here, and then down here, and this x value was when x is equal to 5. And maybe this is what our function looks like. F of x is equal to drawing a blank here. Let's say x plus 1. So it looks like x plus 1 when x is not equal to 5. And it's equal to 1 when x is equal to 5. Now the 1 I'm referring to is if I went straight over from here, we'll pretend that's 1. Okay. And I didn't draw this to scale, so don't like start doing tick marks and say, hey, your graph's not right. I know it's not right. Well, I don't think it's right. Okay. Now, if I were to take a look at each piece, x plus 1, that's a polynomial, it's continuous everywhere, there's no discontinuities. 1, well, that's a line. That's continuous everywhere. It's actually a point when we look up here, but these right here, there's no discontinuities. Okay, so then we check where it changes over. So we plug in 5. Well, 5 plus 1 is 6. There's no x down here, so this is 1. So they're not the same. So they are a discontinuity. That doesn't change. Again, what I did, if you plugged in x equals 5, here you have x plus 1, here you have 1. So I have 5 plus 1, which gives us 6. And, well, this is just 1. So they're not the same, so that is a discontinuity at x equals 5. But if I look at this, Remember what I said earlier, if you can just draw a point here and it'll make it continuous, then it's removable. So this is the one example or where you have a removable. And that'll occur when you have the x not equal to and x is equal to, like you see here. And this is a single number. Which, now that I say that, that should always be a single number. Hopefully that's a correct statement. We'll pretend it is if it isn't. And let me save that. Sometimes you make absolutes like that, and there's always that one exception that you weren't thinking of when you said it. So that's my disclaimer. So if you come up with that example, then I'm covered. There we go. And I believe that was the last problem. So I've already stopped the videos. There we go. And let's stop the other one.